Welcome to today's central exercise class in Mathematics 2. Today we'll be discussing sheet number 12, and as usual, we'll be happy to answer your questions. Please ask any questions you might have on chat.tum.de, and please use this channel here, MA9714-CE. As usual, the chat is moderated by Alan Carlson. As I said, we'll discuss sheet number 12. So this is sheet number 12. There's one problem on line integrals. That's the first one. Then we have a little bit about vector fields, basic stuff. And then a problem on integration over vector fields. That's 12.3. After the discussion of this sheet, I'll also say a few words about the test exam that will start after this central exercise class at 16:30. And of course, I'll be happy to answer questions about the exam as well, but we'll postpone that to the end. So there'll be time at the end for your exam-related questions. Okay, so let's start with the exercise sheet then first. We'll start with 12.1. Here we have a cylinder of radius 2 around the center. This is the center, 1, 2. The base is a circle around the center. And the question is, we have this cylinder here and we cut it off at the top, not by a straight plane parallel to the x1, x2 axis, but instead by the surface of a function, and that is the function f here, by the surface of this function. So basically, that's a plane that's skewed a little, something like this. This cuts through the cylinder. And the question is, what is the lateral area? So the area, basically this area here around the cylinder. And basically that amounts to computing a line integral. That's what we'll do first. So C12.1. Again, all we have here is, let's say this is the x1, x2 plane. This is x3. So this is x1, this is x2, and we have 1, 2. So the center is about here. And we have a circle around that center. That's the base of that cylinder. And the cylinder is on top of that. So something like that. But instead of this even plane here cutting it off, we cut it off with the function f. So the real cutoff will look something like this, right? So here's that surface of the function f of x1, x2. And that happens to be a plane here. Of course, any other function would do as well. And what we're interested in is the lateral area. So the area defined here on the side of the cylinder, basically. This area, and of course on the back side as well, right? So that area around the cylinder, that's the area you want to know. And again, f is the function 2x1 plus 3x2. So what we have to do basically is we consider this line here in the plane, in the x1, x2 plane. And we want to compute the area between that line and the graph given by f restricted to that line. So what we want to compute is actually the line integral of f over the cylinder base. That's the area that we want to compute. And of course, that's true because all the points of f are above the x1, x2 area. If there were points below, then of course we would get negative values and then we would have to deal with absolute values. We don't have to do this in this case. Everything's positive anyway. Okay, so basically we need to compute that integral. And of course, to do so, we first need some description of the curve. So let's try to parameterize that curve. Gamma, and that is the boundary of the base. Now, basically, as I said, this is a circle of radius 2. It's given in the problem description. So a circle of radius 2, that can be written as 2 cosine of t, 2 sine of t. And then the origin is not the center of that circle, but instead the center is supposed to be the point 1, 2. And this here is, of course, centered at the origin. So we take that circle and we shift it so that the center is 1, 2. And we can simply achieve this by adding the point 1, 2 to all of that. So that is a circle around 1, 2 of radius 2. And of course, the parameter space t would then be from 0 to 2 pi. We need one full rotation of that circle. Okay, so that is the curve that we have to deal with. And now we want to compute the curve integral of f of x1, x2 ds along the curve gamma. By definition, that's the same thing as f evaluated at gamma of t times the norm of gamma prime of t dt. And t varies between 0 and 2 pi. So in the parameter interval. Okay, so let's compute this gamma prime here first before we go on. Gamma prime of t is then, here's gamma again. So gamma prime would be, well, we have to differentiate the cosine first. The derivative of the cosine is the negative sign. So that's minus 2 sine of t. And here we have 2 times the sine. The derivative of the sine is the cosine. So we get 2 times cosine of t. And that constant part here in the beginning, of course, that just vanishes. There's no t involved here. Right, so that is the derivative. And that means our integral comes the following. Let's see. Remember, f was the function 2x1 plus 3x2. And so f of gamma of t, this here is gamma of t. So what we need to do is we need to evaluate f at gamma of t, and that is 1 plus 2 cosine of t and 2 plus 2 sine of t. And then we want to multiply this with the norm of gamma prime. Here's gamma prime. So the norm of gamma prime is then the square root of, well, this entry squared plus this entry squared. So that's 4 sine squared of t plus 4 cosine squared of t dt. Now let's use the definition of f here, this one, to compute that value. So what we get is simply the integral, this boundary, sorry, 0 to 2 pi. So we get the integral of 2 times the first coordinate, 1 plus 2 cosine of t, plus 3 times the second coordinate, 2 plus 2 sine of t, times, and for that square root, well, we have the factor 4 that we can factor out. The square root of 4 is 2, so we can just take out a 2. And then we're left with sine squared plus cosine squared. And as you all know, this here is, of course, 1. Right, so that part basically vanishes. So what do we get from that function? So let's see, here's 2 plus 6, so that's 8. And then we get 2 times 2 cosine of t, so that's 4 cosine of t plus 3 times 2 sine of t, so 6 sine of t. And here we have times 2 dt. Okay, so that's something that we can't integrate. Let's just take out the 2 here, and then we have the integral, well, 8 integrated with respect to t, that's simply 8t. Then the cosine of t, the integral of the cosine is the sine, so we get 4 times sine of t. And the integral of the sine is the negative cosine, so we get minus 6 cosine of t, t from 0 to 2 pi. And now we just have to substitute the boundaries. So that's 2, and let's see, 2 pi first, 8 times 2 pi is 16 pi, plus the sine of 2 pi is 0, so that's a 0, minus the cosine of 2 pi is 1, so minus 6. And that's the upper bound. And for the lower bound, t equals 0, we get minus 8 times 0, that's 0. Minus 4 times the sine of 0. Sine of 0 is also 0, so minus 0 again. And then minus, so we get a plus. 6 times the cosine of 0. Cosine of 0 is 1, so we get a plus 6 here. So all in all, we have 2 times 16 pi minus 6 plus 6 cancels out. So the end result is 32 pi. And that's the area that we're looking for. Okay, questions on this problem here?
So far, I don't see any questions. Very quiet.
Wonderful. Then let's proceed to discussing vector fields. C13.2. Oh, sorry, 12.2. Not quite a 13 yet. So this one is about basics of vector fields, so how to sketch a vector field. The first one is a vector field defined on R2 with the exception of the origin. And the vector field is simply defined as x over the norm of x. That's also why 0 is excluded. And as you can see, this one has a specific property. So v of x is x over the norm of x. And if you compute the norm of that vector field at any given point x, then what we get is the norm of x over the norm of x. So the norm is always 1. That means the vectors in this vector field have length 1 at any point. And where are they pointing? Well, they're pointing in direction x. So basically in the direction of the point itself. So they're pointing in radial direction from the origin to the point, and that is the direction. So we can sketch that vector field pretty easily. All right, so basically that looks like this. Nothing at the origin, that's excluded, but anywhere else, let's say we take this point here, then the direction is given by this point itself, and the length is always 1. So that would be the vector attached here. We're taking this point, the direction is given by this connection here. And of course, we have to attach the vector at the point itself. And again, the length is 1. All right, so that's how that vector field will look like. Draw a few vectors here and here and here. And then as we move outwards to points farther away from the origin, the picture remains the same, right? If we attach vectors here, for example, again, same thing. always length 1. So here, and let's say one more here, maybe one here, one here. It's always the same thing. It's always a vector of length 1 pointing away from the origin. So that's how that vector field here looks like. If you want to draw in with a few more vectors, I've plotted this, and you can also find this in the suggested solutions. So this is how a plot will look like. Right? You can see the vectors all have the same length. They all have length 1, and they're always pointing away from the origin in the direction of that particular point. Okay, any questions about this vector field?
There is a general question about how many vectors and like points and vectors should they draw in the exam for such a question?
Yeah, there's no general answer to this question, unfortunately. Sufficiently many so that you can see the characteristics of vector field. So, I mean, in this case, of course, you wouldn't have to draw as many vectors as I have drawn here. Basically, the vector field is pretty boring. Nothing interesting happens here. It all looks the same, right? So just a few vectors would be sufficient. If anything happens, however, then that should be obvious from your sketch. So if, for example, there was another point where all the vectors would converge to, then you should draw some vectors around that point. If they're swirling around a certain center, you should draw sufficiently many vectors such that one can see that swirl. If they change their length, you should draw some so that one can see how that length change happens. Yeah, so basically it's about finding out what the interesting characteristics of a vector field are, and then drawing enough vectors to represent that. It doesn't have to be many, you just have to choose them wisely.
Okay, and then there's a second question. So it looks like the vectors in the bottom left quadrant hit 0, 0. Is that intended?
They shouldn't actually. Yeah, maybe
one.
that one is a bit off here. This one, yeah.
Yeah.
What do you mean? Yeah, that shouldn't be anchored at 0. There is no vector at 0. But of course, there are vectors arbitrarily close to 0. So probably that's one of those.
Okay, I think that's it.
Okay, then let's take a look at B. So in B, we are given a function f, this one here. And the task is to draw the gradient field of f. So f is x2 times e to the x1 plus x2. x2 times e to the x1 plus x2. And we want to draw the gradient field. So let's first compute that gradient. F of x1, x2. Differentiating with respect to x1 only appears here. So that means the derivative with respect to x1 is simply x2 times e to the x1 plus x2, and that's it. And for x2 appears here and here. So we have to use product rule. And that means if we first differentiate with respect to this factor here, we get e to the x1 plus x2, and then plus x2 times, and now we differentiate this factor here for x2. That's simply e to the x1 plus x2. So you can see that we can extract that factor e to the x1 plus x2. And then we're left with x2 and 1 plus x2. And with this part here is responsible for the direction of the field and for part of its length, of course. So that's direction. And this factor here in front, that only influences the length of the resulting vector. So what we can say about the direction already is it only depends on x2. right? It does not depend on x1. So a shift in x1 direction does not change the direction of the vector field. It does change the length, however. x1 influences this factor here. And that's an exponential factor, so that will mainly govern the length for large values of x, right? So with x1 and x2 going positive, as these grow, then this factor will also grow exponentially. And that means the vectors will get longer and longer very fast if we move in x1 direction and x2 direction or x2 direction. And if these numbers become negative, or this sum here becomes negative, then that will be a very small number. So the vectors will become very, very small quickly. Okay, so basically what does that tell us? Well, if you want to draw this vector field, then what we know is that for negative numbers, the vectors will become very, very small. For positive numbers, they will become very long, very quickly. A shift in x1 direction doesn't change the direction of the vectors. And we know it's the gradient field of a function. So if we know something about the function, then in other words, what I want to do is I want to correlate a plot about the function with that gradient vector field. And we already know that a gradient points in the direction of steepest local ascent. So basically that's what this gradient is going to do. If we have that function and we know where it's growing and where the level sets are, then we will get a rough idea of where those gradients are and in what direction they will point. So one possible strategy to plot a vector field would be to first plot a level plot of that function, or get a rough idea of what the levels of that function are. And of course, well, this is basically an exponential function here and some x2 involved, so it's not that easy. But what you can see immediately is that for x2 equals 0, the function value will be 0, right? So there's a very quick sketch here. We can immediately say that for x2 equals 0, the value of f will be 0. So here's undoubtedly a level set, and that level is 0. And if we then have a look at some other values of x2, then we can see that basically for a fixed value of x2, this is an exponential function in x1. So if we fix like a positive value of x2, then we get something, some lines that look basically that look like this here. Yeah, it's too steep. Yeah, so these are levels of that function. And for negative values of x2, we get a negative value here. And now depending on how negative the value is, of course, again, the x1 will partially get us an exponential function. And at some point, that will be balanced off by the x2. So it might be a little harder to get this part of the plot. But basically, that would look like this here. So we have curves, level sets here below the x1 axis that look somehow like this. Once you get that idea, it should be possible to plot the vector field. Again, the vector field, the vectors, the gradients point in the direction of steepest local ascent. So that means they are always perpendicular to the level sets, and they point in the direction of increasing values. So increasing values in this case, well, the values increase in this direction here, and they increase in this direction, basically that way, right? That's the increase. So for example, the vectors here on that line, that would be perpendicular to that line here, and they would point in the direction of increasing function values, so in this direction here, right? So that's one possibility. And now as we're moving along the x1 axis, we said that the length of the vectors depends on x1, but not the direction. So as we're moving along this axis, the direction will always be this. And as x1 gets larger, this length here will dominate, will get larger as well. So these vectors are bound to grow. Well, they will get longer and longer as x1 increases, and they will get shorter as x1 decreases. So they vanish pretty quickly, actually. And of course, you can do the same thing with all the other level sets here. So something like this. And again, they will increase in this direction, they will decrease in this direction. Same thing below here, right? If you want a vector here, for example, that one that would be perpendicular to this axis. So that looks like this. Again, if we go into the direction of positive x1 values, then the length will grow. Oops, that doesn't look very parallel. It will grow. And in this direction, the length will shrink. Right? And again, that's one line here. Okay, so that's basically how that vector field will look like. Purpose of this problem was more to give you an idea of how to correlate level sets, level plots, and gradient fields. And again, let me show you the plot with a few more vectors on that. Yeah, maybe I'd rather use the next page for that. Here we go. And you can see that basic behavior. So again, here's the level sets, right? Here's the one from -2, -1, -0.5, here's 0. And then here you can see those exponential functions, right? And you can also see that the vectors are perpendicular to that, to these lines here, right? When they are attached to those lines. And you can see if both values x1 and x2 become negative, this field here, the vectors become really, really small, close to 0. If they are positive, then the length of the vectors grows very quickly. And for these two here, something in between happens, basically. Okay, that was the idea of this problem here. So that's the plot of that vector field, just to give you an idea of how to approach that and how you can say something about how a vector field looks like. Okay, questions?
Yes, so I have one question. How do you know how the vector field looks like? For example, how to know which part of the function shows the length is the question.
Basically, you try to reformulate it in a way such that it's easy to see how that works. If you don't know, of course, you can always try to compute the norm and then see what the length of the vectors is and what influences that length, right? I mean, here I argued basically that this part here, that's just a real number. So that influences the length, but not the direction. So I can just take that in front of the vector. And of course, that part here also influences the length. But compared to this exponential function, it doesn't play a major role. Yeah, at least not if the values of x1 and x2 get very big or very small. So basically, that's the idea here. I didn't exactly compute the length. I just wanted to get an idea of what influences the length.
Yeah, and I like doing exactly this depends on what your vector field looks like. So it's a little bit, it's not a step 1, step 2 kind of procedure.
Unfortunately not, no. You know, it depends on what the vector field looks like, how it is defined. As I said here, for gradient fields, there's this nice connection to the level sets. So if possible, you should get an idea of what the level sets look like if you're dealing with a gradient field. Otherwise, it's basically trying some creativity. Any more questions? Good.
No, there's one more. It just came in. Do the level sets come from F or the gradient?
The level sets come from F, of course. The gradient is not a function that has real values, so it doesn't have level sets. Right? Level sets are only associated with functions the codomain of which is in the reals. So I can actually remember the level set is the set of all input points that produce a certain value, a certain level. And of course, we can only do this if we actually have levels, meaning real values. So we need a real valued function, so that the level sets come from f, not from the gradient. That's it?
Yeah, so that's as much as I see right now. I think someone is typing, but
let's start with 12.3 and we can always take up more questions later. All right, 12.3. So this one is about integration of a curve in a vector field. So here we have a curve that is given by 2 points, A and B, in 3D space. And the curve corresponds to the straight line connecting these 2 points. So the first task is to determine a parameterization for that curve. And second, there is a vector field given, this vector field here. And the task is to compute the line integral of that vector field along the curve gamma. So let's start with the parameterization here. So we have 2 points. The first is the point A. A is 0, 2, 0. Second is the point B, 1, 0, 0. And we want the straight line between those 2 points. Okay, so we need to find a parameterization that does exactly that. And one simple possibility to do that is to define gamma through taking these 2 points. And defining it as a weighted sum of those 2 points for a parameter that varies between 0 and 1. We take, let's say, 1 minus t times the first point and t times the second point, t in 0, 1. Then gamma of 0 would correspond exactly to that point A, right? That's 1 minus 0 times this first point plus 0 times the second one. Gamma of 1 would correspond exactly to the second point, right? That's 0 times the first plus 1 times the second. And anything in between is a combination of those two, right? So that is exactly how one can parameterize the line, in this case, from A to B. And of course, the problem statement doesn't really say whether we have to consider the curve from A to B or the curve from B to A. So the reverse would also have been fine. And there's other parameterizations. That's not the only possible parameterization, right? You could come up with other ones as well. I think that's a particularly easy one. And we can simplify that a little more by taking it all into one vector. So basically that's t, then here's 2 minus 2t plus 0 and 0. Right, so that's the curve gamma that connects A and B. Questions on that one?
nope, nothing so far.
Wonderful. So now we're considering a vector field in 3D space now. So this is given by 1 over the norm of the vector x to the third times the vector itself. So again, to get a rough idea of how that looks like, this here influences the direction of the vector. This doesn't. So basically, the vectors of that field are pointing in the direction of the point where they are attached to. So again, that will look something like a vector field, like we had that in R2 before, like that here. Similarly, but in R3. Yeah, so basically you get something like balls with vectors pointing outwards. And then you have this vector here for the length. You can see that that's 1 over the norm to the 3rd power. So if you move outwards, the norm gets larger, and that means the vectors get smaller. Whereas if you move close to 0, the vectors become small, and that means this here becomes very large, right? So basically, the length of those, if you want to compute that, the length of v of x in this case is again length of x, and this time over the length of x to the 3rd. So you get something like this, right? So 1 over the length squared. And that means if you get close to 0, then the vectors become pretty long. If you move outwards away from the origin, then the vectors become pretty small quickly. Okay, so that's how that field looks like. And now we're integrating that field along that curve gamma. So we already have the parameterization of gamma that we require for that. We will also require the derivative, because remember the the definition of integrating a vector field along a curve. Definition of this is we integrate over the parameter space t from 0 to 1 in this case of v evaluated at the curve, and then we take the scalar product of that with gamma prime of t dt. So we need to compute gamma prime. Here's gamma, and that means, means gamma prime of t would simply be 1 minus 2 and 0. And then, of course, we also need v evaluated at gamma of t. So that's the first factor here. Let's do that. So v evaluated at gamma of t. So gamma of t is this one, t, 2 minus t 0. V is 1 over the norm to the 3rd times the vector x itself. So we can take out that norm here. That means we have 1 over, well, but the norm is the square root of t squared plus 2 minus 2t squared plus 0 squared. So we get t squared plus 2 minus 2t squared. And then we have to take this to the 3rd. So that's this 1 over x norm to the 3rd. And then we have the scalar product of, well, this part here. That means we just get x1 is t, x2 is 2 minus 2t, and x3 is 0. Right, so that's just t, 2 minus 2t, and 0. And then gamma prime, we've computed that before. Here's gamma prime. That's 1 minus 2, 0 dt. Okay, so let's try to simplify this a little. So instead of writing this complicated fraction here, we could write this as integral of something to the power of minus 3 over 2. And let's see, we have t squared here. And this here evaluates to 4 minus 2 times 2 times 2t, that's 8t plus 4t squared. And now the scalar product here, that's simply t minus 2 times 2 minus 2t plus 0 dt. Okay, so we get integral from 0 to 1 So that is t squared plus 4t squared, that's 5t squared minus 8t plus 4 to the power of -3/2 times, and here we get, let's see, this is -2 times -2 is 4t plus t, that's 5t. And here we get -2 times 2, that's a -4 dt. Okay, so that's the integral we have to solve. Now, how do we solve that? Well, the problem statement already says we should try a substitution to solve that. And the most annoying factor in there is probably this one here. So let's try to substitute that. Let's say this is u. Right? We substitute u as 5t squared minus 8t plus 4. For substitution, we need to compute du by dt. So we need to differentiate u with respect to t. That is, let's say, 10t minus 8. And that means dt is equal to du over 10t minus 8. So this integral after substitution will look like this. Well, instead of t from 0 to 1, we now have u of 0, u of 1 as those boundaries here. Then we have u to the power of -3/2. That's something that we can compute. And we have this 5t minus 4 over, here's 10t minus 8. And there is a du at the end now. And thankfully, this works out nicely because you can see that this here is exactly twice this here. So this all cancels out and we're left with a factor of 1/2. Right? So what we get is 1/2 times the integral. Let's see, u of 0. If we substitute in 0 in here, we get 4. So lower bound is 4. U of 1, that's 5 minus 8 is -3 plus 4 is 1. So upper bound is 1. Then we have u to the power of -3/2. We already took out this 1/2 here. So that's all that is left in the integral. And that integral we can compute. So that's 1/2 times, well, computing an integral like this means you increase the power by 1 and you divide by the new exponent. So what we get is u to the -1/2. And divided by the new exponent. The new exponent is -1/2. So divide by -1/2 means multiply by -2. So we're at that here. And that is from 4 to 1. Let's write a u in here. And finally, we substitute the bounds to get the final result. Upper bound, -2 times, remember, u to the power of -1/2 means 1 over the square root of u. So if we substitute 1, then we get -2 times 1. And then we substitute the lower bound, 4 minus times minus, that's a plus. So we get plus 2 times 1 over the square root of 4, and that's 1/2. So we are left with 1/2 times -2 plus 1. So that is -1/2. And that's the result of this integral here. So, questions?
So there's one question about the parametrization. Why do you start t at 0 and end at 1?
So basically, that depends on how I parameterize. There would have been other choices. What I want here is I want to start my curve at this point at A, and I want to end it at T. So if I start T at 1 and have this factor here, sorry, T at 0 and have this factor here, then that means gamma of 0 will correspond to this point. Gamma of 1 will correspond to this point. I could have done this in other ways as well. And as I said before, the problem statement doesn't say whether we want the line from A to B or from B to A. So both would be valid solutions. And of course, the result will probably change depending on the parameterization that you choose, or the direction that you choose at least.
Okay.
Does that answer the question, or did you mean something
Yes,
else?
I think that answers the question. Or, I mean, feel free to be unsatisfied and ask again. I guess I should say. And then there's a couple of questions, like more general ones. Should I do those and then ask more about this problem if problems show?
Yeah,
like
yeah, of course we can
questions
do
show
that.
up?
Yeah.
So is lecture 13 the last one for this semester?
So the videos have just been posted today, 13th week. They will be the last ones for this semester. Yes, there'll be no new videos next week. But of course, we'll still have exercise sessions next week.
Okay, and then there's a question. Could you maybe explain again how we can see or compute the vector field in 12.2a again?
12.2a, this one here.
That looks like the right one, yes.
Okay, yeah, basically that is a pretty simple one. So what we have is a vector field where the direction is influenced by this here. So X directly gives us a direction. This here is only a real number, so that doesn't change the direction of the field, just the length of the resulting vector. And it's a positive or non-negative real number, so it cannot flip the vector as well, right? So we all know, we know that all vectors, we know that all vectors will point in the direction of the point they're anchored at. So if I take this point, for example, anchor the vector here, I want to find the vector that anchors here. I want to find the vector field, the value of the vector field at that point. What I get is a vector that points exactly in this direction here. So I get something like this, right? Or like this. I don't know about the length yet. And now, of course, I also want to know how long that vector is going to be. And I can just find out by computing the norm of v of x. And it turns out, where the norm of this expression here, this is just a scalar, a real number. So I can take that out of the norm. And that leaves me with just the norm of x itself. So in the end, I get norm of x divided by norm of x, and that's 1. So all vectors in that field have the same length, but it doesn't depend on the point. It's always 1. And that means I have my direction. I know in which direction the vectors are pointing, and now I know they are all length 1. So this will look like that. On the same axis, vectors on that axis will always point in the same direction, and they all have length 1. So this will look like this, right? Vectors on that axis here will point in this direction. And they all have length 1. So this will look like this. Vectors somewhere else, like this one here, again, will point in this direction here. So along that line, the vectors will always point in that same direction. And they will, they will all have length 1. Right? So that will look like this. And so on. And that's how I got that vector field. I hope that helps.
Okay. Yes, he's happy with the answer. So there's also one about 12.1. Didn't we compute the volume under F instead of the lateral area? How would I compute the volume instead?
So we computed the volume under F along that curve here. Right? So it's not the volume of the cylinder, but just the volume of the side of the cylinder, the lateral area. Now we just computed along this curve. if you wanted the volume of the cylinder, we would have to compute the volume integral over this area here, over this disk, not just over the circle. That's the difference.
Okay, and then another question. How would you parameterize a curve through more than 2 points, like in 12.3? For example, if you have 3 different points, is this still easily possible?
That depends on what you want to do. I mean, this is particularly easy because I just wanted a straight line, right? Of course, I could have demanded other curves, but then I would have to state what exactly I want to do. And for 3 points, there's a host of possibilities. For 2 points, there's a host of possibilities already, right? When you have 2 points here, you can take a straight line. That's easy. You can say something like, I want a circle, right? That the center of the circle is somewhere here. So I could say I want a circle like this. You should also be able to do that. Yeah, you know how to parameterize the circle, basically. You know, that's something you could master. I could also say I want something more complex. I want something like this, like a parabola, like that. Yeah. Make up anything you want, and of course the result will differ. I could also take a curve like this, sine-like connection. Why not? And of course, for 3 points, there's also lots of possibilities. Right? You have 3 points. If they happen to lie on a straight line, then you could use that. At least don't quite lie on a straight line. Imagine they would. But that's, of course, that would be a happy coincidence. Let's say we take 3 points that are not collinear. Then one possibility would be to do something like that, but you would need a few more details on how that curve should look like. But you could say that's part of a circle. You could say that's part of a parabola. You could say something completely different, like, I don't know, it's connected by a B-spline, whatever you want. You have to specify what you want here, right? So lots of curves are possible, and you need to state what curve you want.
But if you're given a question with 3 points, for example, it will be stated in a way that you should explain.
Or another possibility,
or you're given a choice.
It might not matter. You're given a choice. That might also be true, yeah. So the statement might also ask for any curve, make up something. And of course, if I was asked to do any curve, I would probably do something like this and this. Seems like the easiest choice. But depending on the circumstances, it might not be. Yeah, it might be more clever to use something else. And last possibility, it might not matter. So if the statement doesn't say what kind of curve we want, then you should think about whether the type of curve will really matter. Maybe there's something in the problem statement that tells you it doesn't matter what curve we use. So you can just come up with one and the result will always be the same. And of course, the same is true if the problem statement asks for a very complicated kind of curve, right? If the problem statement says, I want a curve connecting these that looks like this, then maybe you should think about if the green curve will not possibly give the same result before you try to parameterize the orange one. That's a clever exam question, by the way. Should have thought of that earlier.
Yeah, it's a good one.
Yeah, I've given that away now.
Okay, there's one more. So how would we parameterize a circle?
A circle, simple units where you do know the parameterization of the unit circle, right? That is, depending on what you want, the standard one is usually cosine t sine t. And then you can multiply this by the radius that you want. And that will give you a parameterization of the circle that looks like that. It starts here. So if t is from 0 to 2 pi, of course. That would start here. Then as t increases, the cosine starts at 1, the cosine will decrease, the sine starts at 0 and will increase. So the x1 coordinate decreases, the x2 coordinate increases, so you get a movement like this direction here. So the circle will rotate counterclockwise if you do it like this. And you've also seen already that you can, of course, exchange those two components. So that here also is the parameterization of a circle. And in this case, you're starting again. If we say t is in 0 to 2 pi, and of course we could change that depending on what we want. But if we constrain that from 0 to 2 pi, then that circle would start at 0, 1. So that would start here. Then as t increases, the sign will increase. So the x1 coordinate will increase. So we're moving in this direction. And the cosine will decrease. So we're moving in this direction. Right? And that means the circle will move this way. So this circle will turn clockwise. And of course, there's loads of other possibilities here. You could also say something like, I want my gamma t to be sine of, let's say, 10t and cosine of 10t. Yeah, then basically the rotation will become faster. And of course, t, if you want just one full rotation, then t will now be from 0 to 2 pi over 10. If you want more rotations, that's also possible, of course, then you would let t run more than 2 pi over 10. Or you could also do this here if you just extend the right side of the interval or the left side of the interval, depending on what's more clever. Right? So there's loads and loads of possibilities. I guess that should be sufficient, hopefully.
Yeah, I think that answers the question as well. And then there's one more general. So if we get the mock exam, when will we get it?
Good question. When I'm done.
I don't really know.
Not next week. I won't manage to do that. Hopefully the week after that. At least the week before the exam. That's all I can say. But I try to have it out early. But I mean, if I'm doing a mock exam, it should be close in a way, in difficulty, in length to the real exam. So it will require some care, and it will take some time to come up with a good mock exam.
Okay. And then there's, would it be possible to upload the solutions of the last two sheets a bit earlier so they can ask questions in the Q&As and tutorials?
Yeah, I'll do that. Yeah, I'll upload the solutions for sheet 12 today and for sheet 13 next Monday.
Okay, and that's everything I see. If I have forgotten any questions, then you can repost it. I think that's it.
Okay, then let me say a few words about the upcoming exam. So as you know, as I've already said, we'll be using TUM exam for an online exam once again. So those of you who were already with this course in the first semester and took the exam will be familiar with the system. There's been some improvements, but nothing major. So you should feel at home right away. For those that are new, maybe this is interesting. So I'll just go through the steps once again. And then I'll answer questions about the exam. For those who don't want to listen to that, I've set up a test exam so that you can familiarize yourself with the system, try your equipment, see if everything works the way that you expect it to work, or more specifically, see what doesn't work the way you expect it to work. This test exam will start today at 16:30, so in half an hour. The link to that is available on your TUM online exam registration. There you'll find a link to the TUM exam submission platform, and there you can download the exam starting 16:30. The submission will be open until tomorrow at 10 o'clock in the evening, plus 15 minutes for scanning and uploading. We will not correct this exam. Of course, the participation is completely voluntary, so you can do that. You don't have to do that. And I'm not going to keep any records of who does that or not. So it doesn't influence the final exam and your results in any way, whether you do it or not. We'll also not correct it, but I will have a quick look at all the exams and see if I can find any problems with the scanning, with the submission, anything that you should be aware of. And in that case, I will give you feedback directly. Okay, so that's more meant as a technical demonstration in case you want to test your equipment, in case you want to familiarize yourself with the submission platform that we're going to use. All right, quick introduction to the workflow. So this is basically how a TOEM exam submission works. You first log in to the system. To do that, you use the link that I posted on TOEM Online on your exam registration. You should have gotten an email, by the way, that contains that link. If you didn't, then the reason for that might be that the capacity for your mailbox has been exceeded. I got a few emails bouncing back telling me that this email couldn't be sent because so-and-so exceeded their mailbox quota limit. So please have a look into your mailbox and see if there might be a problem with that. You will want to receive emails from me. Okay, to log in, again, use that link. That is a personalized link, so please do not forward that to anyone else. And to log in, you also need your registration number. Please remember to also enter the leading 0, otherwise it won't work. Then once you're logged in, you should see a list of upcoming assignments for this course here. And currently the only assignment that you'll see is this upcoming test exam. It starts today at 16:30. Select that, and you can then download the sheet, or you'll see a countdown that tells you when the download will start. So that's what you would currently see. Download the sheet as a PDF, and then you can either print that sheet, or you can transfer the sheet to a tablet where you can write on electronically, right, like an iPad, for example. So it's totally fine to work on the exam in an electronic way if you want, or you print that out, whichever works better for you. Write solutions into the sheet, either using an electronic pad or pen and paper. Once you're done, save the result as a multi-page PDF, or use some scanning app on your phone or on your scanner, whichever works better for you, to scan the pages that you've written on. And again, produce a multi-page PDF or a couple of JPEGs. That's also fine. You can also upload more than one JPEG per page. And finally, upload the result on the TOEM exam platform. Right, that looks like something like this. You first add all the files, and then you press upload. And should be aware that you need to press this upload button within the submission deadline. So that means examination end time plus 15 minutes. And then your upload will be processed. That means it will be announced to the server. So the server knows that you have announced an upload in time. And it will automatically be queued and uploaded once the server is ready to accept your solution. So at that point, if you have started the upload in time, you don't have to care about it anymore. Just wait until it's been fully uploaded. And a message like this should appear. And you'd also get a preview of what you have uploaded below, so that you can quickly review that. If you find you uploaded a wrong document, then you can always re-upload as long as you're still within the submission deadline. The last upload that you do will always be the one that is stored on the system. So any upload will overwrite everything else that's been uploaded before. So in case you find you've missed one page, for example, then please do not just upload that one page. Otherwise, that will be the only thing you submitted. Instead, put that page or append that page to the multi-page PDF upload that you have already uploaded before, and then upload the extended PDF once again. Yeah, remember to upload all the other pages. Okay, few notes on software. There's a lot of notes on possible software in the TOEIC exam submission manual that also gives you an overview of that process once again and explains all the steps in more detail. And it contains a few notes on possible software that you can use. A link to that submission manual is on the TOEIC exam submission page itself, and also on the Moodle page in the exams tab. Okay, so that's just a selection of possible apps that have been used in the past for digital editing. For example, GoodNotes, Notability, the Files app on an iPad works. On macOS itself, well, it's probably not a good option as you usually can't use a pen to write on a macOS system. But if you have a digitizer, a small tablet, maybe you want to do that as well. So in that case, the built-in preview app, for example, would be able to do that. On Windows, people have used the Edge browser that also built-in PDF editing capabilities, or an app like Foxit Reader. That's a free app, I think, and PDF Annotator. That's something I have used in the past as well, but that you need to pay for that. It's not that cheap, actually. Scanner apps. So, of course, you can use any scanner that you might have at home. Or if you don't have a scanner, just use your mobile phone. And usually there's a scanner app on that phone already. For Android, we have found that Office Lens seems to work well. For iOS, the Notes app has a built-in scanning functionality. That also works pretty well. And of course, there's a load of possible apps out there that could also do this. Two things to avoid as a scanner app. Cam Scanner seems to be pretty popular, but the results that this produces are pretty bad. I'll show you an example later. So I'd ask you to avoid that software. And also OneNote, that's a digital editing software. I'll show you the problem with that in a minute. So here's some things to watch out when you're scanning. First is try to not cut off anything, right? Rather do a little more margin around it. So here in that case, for example, part of that code is cut off here. Yeah, and that here is, well, a little sheared, so they're also not very well. These QR codes should all be visible. Every page has 3 QR codes in the corner, and those should be completely visible on the scanned pages, because that is used by TOEIC exam to automatically process those pages and sort them in the right way. This is an example used with Cam Scanner, and that does some post-processing that results in QR codes that look like this. And that's a little blurred, as you can see. And this blurring means that TOEIC exam cannot process the code anymore. So again, please don't use that. We can see here is also that's a little blurry, especially down here. So try to avoid that. If you can, try to look for uniform lights if possible. It usually leads to better results. Problem with this one here is there's QR codes from 2 different pages on the same page of the scan. And that should, of course, not happen, right? Because then TOEIC exam will not be able to classify the page correctly. So one page of the original template that you download from TOEIC exam should correspond to exactly one page of the PDF that you upload, or one JPEG that you upload. And here's a result produced by OneNote. And so OneNote usually exports the results in a way such that a one-page PDF is produced. That is just one page that is very, very long and contains all the pages of the original upload. And of course, that also has the problem that all the codes are now on the same page. That doesn't work. And also, what you think about if this was like 20 pages or so, size that the original exam might have, and you can imagine that we will not be able to read anything in that size anymore, right? So we won't be able to correct something like that. So please make sure that in your submission, there's one sorry, there's one page in the resulting PDF for every page in the original download. Those need to correspond exactly. Quick look at the timeline. As I said, when examination starts, you download the sheet, you start printing, or you transfer it to your tablet. And from the examination start, you have 90 minutes to work on the exam. At the end of examination, you have 15 more minutes to scan and upload the results. And that should usually be sufficient. But of course, if you have a very slow scanner, then you might want to start scanning somewhere in the middle already, right? I mean, for the problems that you have done already, you could just put them on the scanners, press start already, and then have those ready once you're done with the rest. So within those 15 minutes, you need to initiate the upload. And once you've done that, just wait until the upload completes. There's 45 more minutes for the upload to complete once it has been initiated, but you need to press the upload button within the 15 minutes. A few notes. As I said, you can upload multiple times, but please be aware of that the last upload always completely overrides everything else. The last upload is always your final submission. The submission end is sharp to the second. There's no exceptions, right? So if the exam ends at 2200, then that means you need to press the upload button until 2200, 14 minutes and 59 seconds. If you press it 1 second too late, then your upload will not be accepted anymore. So try to not use that 15 minutes to the last second. Also, please make sure to test your equipment before examination day. It's usually not a good day when you discover that your scanner is too slow and you're already doing the examination, right? That's a little late. Also, of course, you should set up the processes. You should know how to transfer the scan to your computer and to upload the scan from your computer. That's something that you should have tested before. And that's what the test exam is for. And as I said, start your scanning process early. One note on paper. So in case you don't have a printer and you don't have a tablet, you can also use individual paper. In that case, there is a template available on the Moodle course pages. Please use that template. That contains basically 20 empty pages and a page of instructions of how to use it. Please download that, print it, read that page carefully. And then you can submit these pages instead of the original TOEIC exam templates. And as I said, the submission link for this exam and also for the final exam is on TOEIC Online. A link to the TOEIC exam submission manual is available on Moodle. So please, if you haven't used TOEIC exam before, at least, please give that a read also. For the test exam, I already said this will start today at 16:30, so in about 16 minutes. The examination time of that test exam ends Tuesday, tomorrow, at 10 o'clock in the evening. And that means submission end is at 22:15 or 22:14:59 to be more precise. And then the upload end for this one is set to midnight. So I don't expect any queues at the end, of course, but in case you are being queued when you hit the upload button, then you have some more time to complete the upload. And if you have any questions, any feedback on that test exam, of course, we'll be happy to answer your questions. Use the Moodle forums or use the chat, if possible, to ask your questions here. And as I said already, there's no bonus. There's no significance of this demo on the real exam. In fact, I won't even save that data beyond this semester. All I will do is look at the exams that you submitted and see if I can find any obvious problems with your scanning or submission. And in case I can find something, I'll get back to you. I'll try to write you an email. All right. So that's all I wanted to say. Any questions?
So I don't see, there's one. Can we do the test exam once or more often to compare different devices? Does it always, you can do that one first.
You can upload it as much as you want within the time limit. So until tomorrow at 10, feel free to upload as many as you want.
And does it always take 45 minutes to upload, or is it the max time?
That's the max time. It's just the max time. So usually it takes, depending on your internet connection, of course, a minute or so. Yeah, not much longer. So the 45 minutes is just if 100 people try to upload at the same time, that's not uncommon in larger exams, then the server will assign them a place in the queue and then work through that queue, and that might take a few minutes, usually not more than 10 minutes or so. Yeah, so the 45 minutes, that should be sufficient. It's just the max time that I'll accept. So after that time, the server officially closes all the upload possibilities, and that's when we can actually start correcting.
Okay, so those are the only questions I've seen.
Good.
Guess that means everything is clear.
I do hope so. So then, thanks a lot for attending this session. Thanks a lot to Alind for moderating the chat. And as usual, if there's any more questions, use the forum, use the chat, or of course, use our tutorials every Thursday from 2 to 5 o'clock. You're welcome with any questions about this course, about any sheet that you have problems with, just ask. Okay, so have a nice day, and I'll see you.